Hi, Nick McQuaid here. Welcome to week 4 of iste780, Data-Driven Knowledge Discovery. And in this first day of the week, in this first video of the day, we're going to talk about polynomial regression and step functions, which are two examples of basis functions, which we'll get into more elaborate ones later. So this is our attempt to move beyond linearity. So let's get started. Okay, so we've mostly done linear models till now. We did a little bit with polynomial regression. If you recall, in an earlier chapter, we predicted miles per gallon on the basis of horsepower squared, among other things. And that's an example of polynomial regression. And the polynomial could be x squared or x cubed or x to the fourth. Typically, it's only up to those four. That's usual practice, but it can be any powers of x. So, and this is a simple way to provide a nonlinear fit to data. We're going to look at more elaborate ways. We actually have very briefly looked at more elaborate ways, but we're going to delve into it a bit more. Now, a polynomial regression applies a global structure to the data, and we might want to do something local to different bits and pieces of the data. So another possibility is a piecewise constant function or step function. So we're going to look at that also. Then later we're going to look at splines. We'll look at a couple of different kinds of splines. And then tomorrow we'll deal with local regression and general additive models. Okay, so polynomial regression simply substitutes in place of this model, and we've already seen this model before, and we generally don't use greater than 3 or 4, although there are fields I kind of dispute that. I believe I don't follow cryptography closely, but I believe in cryptography polynomials higher than this are used to model ciphertext, so that may be an exception to that. And basically what we're trying to do is get a nonlinear curve. We either suspect nonlinearity, or we've perhaps done some plotting that shows some evidence in the training data of nonlinearity. So that's our motivation for doing this, is either some suspicion or some evidence. And here's an example. So here's the wage data. So this is age being used as a predictor of wage, and here's a polynomial of the fourth order. So this is age to the fourth power. And the model, let's just look briefly at the model. Here's the full model right here. So it's beta naught plus beta 1 x plus beta 2 x squared plus beta 3 x cubed plus beta 4 x to the fourth. Okay, and that gives us this solid line, this curve here. The two dashed lines are a 95% confidence interval, which is mentioned right here. 95% confidence interval is pretty small until we get out here. Any place where we don't have very much data, the problem is we're going to get very high variance because there's just nothing there. We also have two groups here. So we have this one group that the textbook has dubbed the high earners. By the way, this chapter is written, I think, in a more informal style than the previous chapters, which is nice. Anyway, they dub these the high earners and these the low earners, and draw a line across here to separate them at the 250 mark. Now, I should point out that there are 3,000. This data set has 3,000 observations, and there are only 79 observations above the 250 mark. So when they do this, so this is a logistic regression with the exact same function. So let's just take a look at the logistic regression model. What we've done is taken the familiar logistic regression that we did in a previous chapter and simply plugged in the polynomial function into e to the power of that function over 1 plus e to the power of that function. So when we do that, the event that we're modeling is the probability that a given person is in the high earner category purely on the basis of age. And so we get this ridiculous 95% confidence interval here because there's just nothing. First of all, there's a tiny number of members of this 250 plus category, and there are also very few people in this. Where does it become ridiculous? About 70 to 80-year-old category is pretty sparsely populated. Okay, so but this is a good one thing that's really nice about this curve is that, and you'll see this in comparison with the step function in a minute, is that it very nicely models this increase that you can see over here. See, this area is kind of empty and this area is kind of empty. So we would suspect that there's an increase in wages in these age groups. Now, let's see. So one alternative to this, instead of imposing this global structure, is to do constants. So here, let's just take a look at a picture of a step function, and you can see obviously why it's called a step function, because it looks like steps, looks like stair steps. So what we do is take some category of x's. X is less than 32. If x is less than 32, then we assign the constant 99 to it. If x is from 34 to 64, we assign the constant 120 to it. I'm just guessing. I don't know what that is. But the idea of a step function is this. We have these indicator variables. So here's the examples of indicator variables. So if x is less than the lowest category, so let's say that the lowest category is age 20, then this indicator variable is turned on, set to 1. If x is between 20 and 30, then this indicator variable is turned on, and all the others are turned off. So by turned on, I mean this takes on the value of 1. This function takes on the value of 1. All of these other functions take on the value of 0. If x is between 30 and 40, this is it. If x is between 70 and 80, this is it. If x is over 80, this is turned to 1, and all the others are turned to 0. So what the effect that this has, if we look at the equation for a step function, the effect that this has is we have this model. By the way, that first category, C naught, traditionally doesn't exist. That's what this very long footnote is about. Traditionally, if x is in the lowest category, we just let beta naught be the coefficient. Everything is turned off. If x is in the lowest category, all of these are 0, and then yi is equal to beta naught in that case. And then for each one of these, it's turned on if x is in this region, and all the others are turned off. So then yi is equal to beta 1 beta 1 times 1. So it's equal to beta 1 times 1 because the output of this function is 1. Okay, plus the error term. So here's an example of doing this step function. And one thing that's very obviously a problem with it is that, now I don't know what, it says the step function has been applied here, but does it say, I don't think it says what the categories are, but the textbook makes the point that it completely misses this increase along here, that we just have this constant from here to here. And so it's not a really very good picture of the data. Now, and they've done the same thing here with the logistic regression, applying a step function to the logistic regression and this event of the probability of the event that wages are greater than 250 given age. And again, we have this silly looking confidence interval here because we don't have information here. And typically step function, the textbook makes the point that step functions are used a lot in biostatistics and epidemiology. So if we're trying to, for instance, model the ages at which people get heart attacks or something like that, there's usually a lot of data available to epidemiologists. Now, they obviously would like to be able to work on rare diseases too, and deal with situations where they don't have a lot of data available. But typically, this particular type of technique is used where there is a lot of data, where we're looking at hospitals full of data on people's propensity for heart disease or lung disease or whatever. Apparently, well, I don't want to get into that. So that's the typical use of step functions. Now, you may say to yourself, since this doesn't seem very sophisticated, and these bins are obviously too big, or they look big and unnatural, they don't necessarily do any better of a job than what this did. Why use these? Well, think of things. There are lots of things that can be modeled by age, and propensity for heart attack is one of them. And so we could. So the textbook makes the point that if you make 5-year bins, every bin is a 5-year period, you get a lot of you can get a more sophisticated read. And there are some things that you could model, like dosage, for example, that might only occur in steps. Dosage might not be possible to get data on every conceivable dosage. You have to have a dosage of 10 milligrams or 20 milligrams or 30 milligrams. You have like some sort of limitation on the amount of variability that X takes on. And so there are uses for the step function, but we're going to look at more elaborate ones in the next video, more elaborate versions of this. So these are both polynomial and step functions are examples of basis functions. So here's a more general form that both of those followed. And so if we think about the polynomial regression, so look at each term here, and here's the shape of the term for polynomial regression. Bj of xi is equal to xi to the jth power. Okay, and if we think about the step function, the general form for the step function is just bj of xi is the output of the indicator function. Cj is less than or equal to xi, which is less than or equal to cj plus 1, where plus 1 means the next category. So this is a general way to do things, and so you could think, instead of just applying constants or just applying polynomials, you might be able to do something else with this. You might be able to have standing in here. Oops. I can't really select what I'm trying to select. So for each one of these terms, you might be able to, and remember what we're estimating are these coefficients. We're always estimating the beta in these, so we can apply some previously decided on function in here. And the next video we're going to look at couple of examples of those regression splines and smoothing splines. So thanks for your attention, and I'll talk to you again.